Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today, we are undertaking a deep dive into, well, the pretty dense world of pressure vessel design. We're going to try and synthesize these complex standards, the geometry, the loading procedures.
It's a heavy lift for sure. Our mission today is to really get past the textbook stuff. We're unpacking the critical calculations, the ones that govern how these massive containers are actually engineered for safety.
And for compliance. We're talking standards like ASME.
Exactly, from shell thickness right down to how you bolt them to the ground.
Okay, let's unpack it. Let's start with the absolute fundamentals, the structure itself.
When you picture a pressure vessel, you're usually thinking of a thin-walled cylinder with end closures. We call those heads.
And those heads can be different shapes, right? Ellipsoidal, spherical.
Precisely, ellipsoidal, spherical, or toruspherical. But the physics, it all comes back to thin-walled cylinder theory. And that immediately introduces the two main stresses you have to deal with.
Right. Circumferential, which is also called hoop stress, and then the longitudinal stress running the length of it.
And this is foundational. When you run the numbers PD over 2T for hoop and PD over 4T for longitudinal, you see it immediately.
That classic 2-to-1 ratio.
That ratio is everything. The circumferential stress is literally double the longitudinal stress, which means the vessel is fundamentally weaker around its girth.
So that hoop strength is almost always what drives your design. It's the controlling parameter.
Almost always. It has huge implications for how you build it, especially the welds. The quality of that long longitudinal weld is absolutely critical because it's holding back twice the force.
Okay, that makes sense. The weakest link. Let's stick with geometry for a second, though. Those 2.1 ellipsoidal heads are super common, but they're not simple, are they?
Not at all. This is where simple formulas meet real-world complexity. Under pressure, the cylinder part wants to expand outwards.
Yeah.
But the ellipsoidal head actually tries to contract, especially right near that junction where it meets the shell.
So you have two parts literally fighting each other at the weld seam.
Essentially, yes. And that creates these very high localized bending stresses. If you actually map the hoop stress in the head, you see it flip from tensile pulling out to compressive.
Pushing in.
Right. And that compressive stress introduces a really nasty failure mode, local buckling.
And that's why just knowing PD over 2T is not the end of the story.
Not even close.
Okay, let's move from the shape to the numbers that get stamped on the nameplate. We hear MAWP, MAP, design pressure. They sound similar. What's the functional difference?
The one you really need to remember is MAWP, maximum allowable working pressure.
And that's the limit for the vessel when it's what?
When it's in its hot and corroded condition. It's the safety limit that's calculated after you've already subtracted the corrosion allowance from the thickness. It's the true operating ceiling.
Got it. So it already factors in future damage.
Exactly. The relief valves have to be set to that number. Now, MAP, or maximum allowable pressure, is a bit different. That's the limit for the vessel when it's new and cold, uncorroded.
So why do we even need that one? Isn't MAWP the only one that matters for safety?
You need MAP mostly for testing. The hydrostatic test pressure, when the vessel is first built, is based on MAP. You test it at a higher pressure to prove its initial strength.
And design pressure.
That's just the number you use for your calculations. It's the worst-case combo of pressure and temperature you expect in normal operation. It's what drives the initial math.
Okay, you mentioned temperature. That brings out the MDMT, the minimum design metal temperature.
MDMT is crucial. A lot of steels get brittle at low temperatures. If your vessel is going to operate in a cold climate or with a process that gets cold, you have to make sure the material doesn't just shatter on impact.
So what's the fix? A different material.
That's one option. But it creates this iterative decision tree for the designer. You can use a more expensive, tougher alloy, or you could just make the shell thicker, or you can just decide to do expensive impact testing to prove the cheaper material works.
It's an economic trade-off.
It's almost always an economic trade-off.
Which leads us perfectly into optimizing the whole vessel. The length to diameter ratio, the LD.
Yeah.
How do you find the cheapest shape for a given volume?
Well, theoretically, the most efficient shape is a sphere. Maximum volume, minimum surface area.
But you almost never see giant spherical process vessels. Why not?
They're a nightmare to build. Forming thick plates into perfect spheres, welding them, it's just incredibly expensive. Cylinders are much, much easier to roll and fabricate.
So for a cylinder, what's the sweet spot? The most economical LD?
It's generally somewhere between 1 and 10. For a simple atmospheric tank, it's actually 1. But for your average pressure vessel, you're usually looking at a ratio between 3 and 5.
And what pushes you toward 5 instead of 3?
Things like higher pressure or a larger corrosion allowance. But practically, a vessel in that 3 to 5 range is also easier to transport and support against things like wind, which is a whole other problem.
Let's get into that. External forces. First, let's clarify two failure modes. Buckling versus collapse. They sound similar.
They're very different. Buckling is a local instability. Think of squeezing an aluminum can until one spot suddenly wrinkles or dimples. That's buckling. The force that causes it is always less than the material's actual compressive strength.
It's a failure of geometry, not just material.
Perfectly put. Collapse, on the other hand, is a general failure of the entire cross-section. The whole thing just flattens, usually due to external pressure or a vacuum.
And to prevent that, we see stiffening rings on the outside of some vessels.
Right. Those rings are another economic choice. You could just make the shell super thick to resist buckling, but that's a lot of steel. Or you could use a very thin shell with tons of rings, but that's a lot of welding labor.
So you find a balance.
You find a balance. For vessels up to about 8 feet in diameter, you'll often see rings spaced at about 2 times the diameter. For bigger ones, it's closer to 1 diameter.
Okay, now for the really big external forces. Wind and earthquakes.
These are lateral forces, basically trying to tip the vessel over, and the codes for calculating them are incredibly specific. For wind, you have to start by classifying the structure. Is it category I, like a barn with a low hazard to human life? Or is it category 5, an essential facility like a hospital?
And a hospital would need a much higher safety factor.
A much higher factor. Then you look at the exposure category. Is it in open terrain or right on the coast where winds are stronger? All these coefficients feed into the final design wind pressure.
It's very site-specific. And for seismic.
For seismic, the key calculation is the base shear, V. It's a function of the vessel's operating weight and a seismic factor for that specific geographic zone.
And there's a little gift from the ASME code here, isn't there, for these kinds of loads?
There is. The code allows a 1/3 increase in the material's allowable stress for wind or seismic loads.
Why is that?
Because they're short-duration, transient loads. The material can handle a brief spike in stress without permanent damage, so the code lets you take advantage of that. It saves a lot of material and cost.
A great example of balancing safety and economics. Okay, let's talk about how these things actually meet the ground. Supports.
You've got a few main types: skirts, legs, saddles for horizontal vessels, lugs.
For a tall vertical vessel, the skirt is pretty standard. What determines how thick that skirt needs to be?
It's a combination of things. The load during erection is a big one. Also the anchor chair design, any openings you have to cut in the skirt, and of course, the total weight plus the overturning moment from wind or seismic.
And for horizontal vessels on saddles, the design method is old.
It is. Zick's analysis from 1951 is still the cornerstone. It's based on the assumption that the saddles are rigid, which isn't perfectly true, but the model has proven to be incredibly reliable for decades.
And the rule of thumb for placing them.
You generally locate them near the heads, within about 1/4 of the vessel's diameter from the end. You're taking advantage of the stiffening effect from the curved head.
Okay, what about transportations? This is where things can go really wrong.
Absolutely. If a vessel is over 50,000 pounds or has an LD ratio over 5, you need a specialized lifting analysis. You have to analyze 2 completely different load cases just for tilting it upright.
What are those?
When it's horizontal on the ground, the load is shared between the top lifting lugs and a tailing lug at the base. But as you lift, you pass a point where the entire crushing weight of the vessel is hanging only from those top lugs.
They better be designed for that.
If they're not, the lift ends very badly.
And for shipping it on a truck, I've heard there are strict rules about the number of supports.
Yes. You use only 2 shipping saddles, period.
Why only 2? Wouldn't 3 be more stable?
You'd think so, but it actually creates what we call a statically indeterminate structure. You have no idea how the load is being shared between the 3 points. A small bump in the road could put the entire weight on the middle saddle and buckle the shell.
So 2 points keeps it simple and predictable.
Exactly. And you only lash it down over the saddles, never on the shell itself.
Okay, finally, let's touch on the regulatory world that enforces all of this. In the U.S., it's all about ASME certification.
The ASME stamp is the proof of compliance. The manufacturer issues a data report, and the vessel gets a physical stamp. S for power boiler, key P for pressure piping, and so on.
And in Europe, there's the PED, the Pressure Equipment Directive. How does that work?
The PED classifies equipment based on risk. It looks at the product of the maximum pressure, PS, and the volume, V. The higher that PS times V number, the higher the risk.
And risk also depends on what's inside it.
Right. Group 1 fluids are the dangerous ones, flammable, explosive, toxic. Group 2 is everything else, like steam or air. Those two factors, the PS times V and the fluid group, put the vessel into a category from I to IV, which determines how much inspection and quality control is required.
This has been wow. It's clear that designing one of these is a massive effort. So many iterative calculations and rigid codes.
What's really fascinating to me is a tension you see now between the old school and new school methods, designed by formula or DBF, using those classic equations we talked about.
And designed by analysis or DBA.
Exactly. DPA uses finite element analysis and powerful software. It's essential for unusual shapes or when you have to combine complex loads like wind and seismic in a way the old formulas just can't handle. It lets you push the boundaries while still proving safety.
So what does this all mean for you, the learner? It means every high-pressure cylinder, every head, every single weld you see out there is the result of this intense, calculated balance. It's an engineer walking a tightrope between absolute regulatory compliance on one side and the constant economic pressure to use less material on the other. That safety margin you rely on is the direct result of hundreds of these small decisions, all aimed at predicting and preventing failure before it can ever happen. That's it for today, Design Junkies. If you're getting something out of this, follow the podcast and leave a review. It helps the whole family grow, learn, and build better together.